Well, how are you doing? This video is going to be about aircraft pitch. I have made videos on this in the past to do with the chord line and angle of attack. This is going to be a slightly more fuller version with some extras in it, and there will be a good bit of reading, but also some diagrams in between. And I hope I know that this will inform a lot of people. Okay, let's get stuck into it. So we don't have too long of a video. Okay, aircraft pitch. The pitch of an aircraft, also known as its angle of attack, is determined by its airspeed. What I mean by this is that the airspeed of an airplane will determine the correct pitch to hold that airplane at. So any reasonable change in airspeed will result in a change in pitch. Explanation. An airplane at takeoff creates lift due to two things. The first is thrust, which causes a downforce on the tail of the aircraft, and the second is manipulation of the elevators at the tail, adding to this downforce being created by the thrust. This results in a change of pressure just above and below the leading edge of the wings, with positive pressure being created just under the first quarter of the leading edge of the airfoil's wings. This positive pressure pushes the leading edge of the wings upwards, as this positive pressure is trying to equalize with the negative pressure above it. As the positive pressure is high pressure and the negative pressure is low pressure, and as we know, high pressure will always flow to low pressure. This is what creates the lift effect in an aircraft, as the leading edge of the wings are being tilted upwards, pitched up. This is officially described as the chord line of the wings being pitched above horizontal. The chord line is an imaginary line that runs through the center of the wings and is used as a benchmark for the aircraft's pitch-lift relationship. When the chord line is pitched above horizontal, this is described as positive lift. When it is pitched below horizontal, this is described as negative lift as a basic. Some wings act differently than others though, as a cambered wing will still hold more positive than negative lift when it is pitched 2 degrees below horizontal. But the but here is because yes, a cambered wing will still hold more positive than negative lift when pitched 2 degrees below horizontal, and will still hold a small amount of positive lift when pitched as much as 5 degrees below horizontal. But there is some mitigating factors here, and they are that once a cambered wing goes further than minus 2 degrees below horizontal, it will lose its positive to negative lift. Lift dominance. As at minus 2 degrees, there is maybe a 60-40 positive dominance. But by minus 2.5 or minus 3 degrees, that balance shifts the other way, giving the negative the 60-40 dominance. So all this really means is a more controlled descent. The reason I say that this only results in a more controlled descent is because regardless of the type of wing airfoil being used, any pitch that is -1 or below is officially called a descent towards the Earth's surface. So yes, a cambered airfoil can hold more positive lift than other types of wings, but that does not change the physics of the situation. As any pitch, regardless of how small, that is below horizontal is officially considered a descent. So could a cambered wing help a pilot have a more controlled descent? Yes, of course it could, but I am sure it is a very popular wing for descending with. Other types of airfoils wings will lose all positive lift once the chord line reaches 0 degrees horizontal and below, as they cannot hold positive lift unless they are pitched up above the horizontal. As an aircraft flies, the more thrust that is imparted by the pilot will result in more downforce on the tail, which will create more positive lift, but due to the positive pressure being mainly under the front quarter of the leading edge of the wings, this will cause an upward tilting of the wings and the nose of the aircraft. So as a pilot has thrust, they must also control the pitch. This is why when a jet fighter flies fast, they keep the nose pitched at about +2 degrees above horizontal, and when they are coming into land, they will have maybe a +10 degrees pitch angle above horizontal. This is also the reason why commercial aircraft fly with a pitch angle of between +3 and +5 degrees above horizontal when flying at cruising altitude. As the faster a plane flies, the more positive lift it gains, and the slower a plane flies, the less positive lift it gains. And that is the reason for a +2 degree pitch when flying fast and a +10 degree pitch when flying slow to land. The pilot must change and control the pitch angle in accordance with the airspeed. So when flying fast, the airplane must have its nose pushed down to stop the positive lift from creating an upward stall due to too great of a pitch angle upwards. And when flying slow, the pilot must keep a high pitch angle as there is less thrust being imparted, so raising the pitch angle will create positive lift and keep the airplane in the air. Moving fast creates lift, so less pitch angle is necessary. More important is the control of the lift when flying fast. But moving slow doesn't create as much lift, so a higher angle of attack is necessary. So the basic rule is more thrust, less pitch, and less thrust, more pitch. Okay, second now. Okay, so this is a basic indicator. I'm just going to make it a bit bigger now. So this is a basic indicator. This is not just pitch though. There is an angle of attack indicator, but this is for banking and other things. This white line here, this is the horizontal, right? This is the baseline horizontal. The orange dot and the two orange lines here, they represent the aircraft, and these are the wings. So when the aircraft is pitched above horizontal to fly horizontally, as it has to be. To fly horizontally, an aircraft has to have the chord line of the wings pitched above horizontal. So during flight, these orange lines will be slightly above this white line. So you could say if this was 5 degrees pitch here, which it is shown to be, you would probably have these orange lines about maybe halfway or a bit over between this horizontal line here and this 5 degree line here. And that's where it would be for the majority of it would stay within that parameter while cruising at cruising altitude all the time. So regardless of the length of the flight, that is, as long as the plane is at cruising altitude, the orange lines, as long as the plane is flying, basically, once it's not taking off or landing, it'll be between those two parameters that these orange wing lines here will be, because that's where it has to be. To fly in a horizontal fashion, the airplane has to have the chord line of the wings above horizontal. That's just the dynamics of flight. Okay, this here is, I'll just get rid of this thing here. I'll ignore it. So this is, it won't go away. This here is just showing the chord line and different ascending level flight and descending with the use of the chord line, or sorry, with showing the relationship between the chord line and the horizontal. So you can look at that yourselves, and I'm not going to go into it too much because the next two are more simplistic, and I want to show them. So so angle of attack, right? Flying slow, right? The angle of attack is high when you're flying slow, because the pilot has to have a high angle of attack to keep enough lift. When at cruise speed, the angle of attack is moderate, right? So these arrows here are horizontal, and this is the angle of attack, right? Cruise speed is moderate, slow speed is high, and high speed then will be a shallow angle of attack. We'll be talking about this is about 2 degrees above horizontal. So it will still be above horizontal, but it will be not as high above as at cruise speed or slow speed, as there isn't a necessity for it. And because the pilot is adding thrust, they must keep the nose down, because otherwise it will go up and into a possible stall. So this one is not as clear, but I'll try and show it anyway. I won't make it any bigger because it's hard to read it. So this shows here at 150 knots airspeed, there will be a 3 degree angle of attack. At 100 knots, there will be an 8 degree angle of attack. At 80 knots, there will be a 12 degree angle of attack. And at 60 knots, there will be an 18 degree angle of attack. So as you can see, the more speed, the more shallow the angle of attack is. They have to have it like that. So, and the less speed, the greater the angle of attack, because they have to have it like that. But to fly at all of these, as you can see, all of these diagrams, they're all showing the chord line of the wings, and then obviously the nose tube of the aircraft above horizontal. That's the horizontal line. These 4 lines here. So they're always flying with the chord line above horizontal. They have to, otherwise they can't fly. It's that simple. Okay, so I'll read this first top line again because it's important. So the basic rule is more thrust, less pitch, and less thrust, more pitch. The pilot balances these two things by keeping a balance between the amount of thrust he or she is imparting and how much manipulation of the pitch angle they need to execute through the use of the aircraft's elevators at the rear. What pilots don't do is fly at cruising altitude with their pitch angle below horizontal ever. They never do this, as then two things would be happening. One, they would be losing the necessary positive lift to keep the aircraft up in the air. Two, they would be officially descending towards the ground. What that means is that if they were flying with the angle of attack below horizontal, then them two things would be what would be happening. They would be losing the necessary positive lift to keep the aircraft up in the air. So even with a cambered wing, once the chord line goes below zero, you're losing positive lift. And then number two, they would be officially descending towards the ground. So, like, no matter what way you work it, as soon as the chord line of the wings goes below horizontal, it is officially descending. And that's that. You can't go from one horizontal to another horizontal. Horizontal is a constant. You can't violate it. You can't violate horizontal and still be horizontal. You can't go pitch below horizontal and call some other thing a horizontal. That might be a straight line, but it's not horizontal. There is only one horizontal, and it's always a constant. So as soon as you pitch below it, that's it. You're not flying horizontal. You're not above horizontal. You're going to lose positive lift. It's nonsense. They don't do that, because these two things will be happening. They would be losing the necessary positive lift, and they will be descending, because that's what would happen. So they don't do that. What I have detailed so far in this presentation is the basic reality to how an aircraft's angle of attack works, what positive and negative lift is, and how lift is created or lost through the use of thrust and pitch. But we have a claim from some pilots that they are flying around the globe Earth with a radius of 3959 miles as an average. So if we test this claim against reality, we will see that in reality a pilot will not fly at cruising altitude with the chord line or nose of the aircraft pitched below horizontal, something that would be a necessity for a pilot that was to fly over a spherical surface. And to prove this, I will show some pitch mathematics that are based on what a pilot would have to do if they were to fly over a globe Earth with a radius of 3959 miles as an average at cruising altitude, travelling at a constant 550 miles per hour and an airspeed that would be fairly common for a commercial airliner. Okay, I must say thanks to my friend Adam Meakin, who helped me out with this, because my mathematics doesn't be brilliant sometimes. Okay, at 550 miles per hour airspeed, a pilot flying over a globe Earth with an average radius of 3959 miles would have to be pitching down below horizontal minus 0.0025% of a degree every second. This doesn't seem like much, it seems like a tiny amount, but there's a huge problem here. Firstly, aircraft don't fly with their pitch angle below horizontal while at cruising altitude ever, as the aircraft would be losing the necessary lift it needs to fly, and it would be officially in a descent then. So these two facts should be enough to sway anybody at this stage against the idea that aircraft are flying over a globe Earth. But as people can be very stupid and dogged, they will take the minus 0.0025% of a below horizontal pitch per second angle correction, something that will be a necessity to fly over a globe Earth with an airspeed of 550 miles per hour, and just write it off. Right? Because people don't want to live in reality. So they go, we'll just write that off. Right? But you can't just write that off. And I'm going to show you why you can't. Not only would you not have any lift with your angle of attack pitch below zero, and you'll be heading in, and you're also in a descent towards the ground. But there's a bigger problem. But what they are not accounting for is the accumulation that this pitch correction would create. As a minus 0.0025% per second correction would result in a minus 0.15% per minute below horizontal correction, or a minus 9 degrees below horizontal pitch correction per hour. Remember, to fly over a globe Earth with an average radius of 3959 miles, then the pilot can never fly horizontally, as they must always have a below horizontal pitch. And to fly horizontally, in reality, they must fly with the nose of the aircraft above horizontal. They can't fly with the nose or the chord line below horizontal, as they won't have lift. And it'll be also a descent towards the ground. So it's complete and utter nonsense to think that they can fly and pitch down and fly and pitch down. They can't do that. And I'm going to show you why they're not doing it as well. Not that I don't think anyone with good faculty of mind won't need to know, but there's still people out there who will still be arguing at this point. Pilots will follow an altitude, which means that they will try to hold a constant even distance above the Earth's surface through the referencing of the outside air pressure. So to do this around the globe Earth would mean either a constant downward pitch below horizontal or constant sharp pitch corrections downwards throughout a flight. And this would mean that all passengers and crew would need to be seated and have their seatbelts strapped on for the majority of the journey. But this does not happen, as the aircraft stays flying with its nose and chord line +3 to +5 degrees above horizontal at all times at cruising altitude. So what this means is pilots follow an altitude, but above a globe Earth, the altitude, right, would have to be constant, right? And so to fly around the globe Earth and follow an altitude would mean that you'd have to constantly be pitching down below horizontal. That's the only way you can do it. That is the geometry of a ball or a circle. You can't fly horizontally and stay at the same, let's say at the same, although parallel lines are straight, you won't stay anyway, let's say two curved parallel lines. You're trying to make a second curved parallel line with a second curved line in parallel with a curved line underneath you by trying to follow an altitude around the globe Earth. So how are you going to do this and not pitch down below zero? It would be impossible. It's a physics impossibility. You have to pitch down below zero, otherwise you won't be able to follow this altitude. So if they're flying around the globe Earth and following an altitude, then that means they have to be pitching down below zero, which would mean an accumulation of 9 degrees below zero pitch after an hour. And that's only 1 hour. But they don't do that. They fly with the nose and chord line above horizontal, 3 to 5 degrees at cruising altitude. That's what commercial airliners do. So this is nonsense. They can't follow an altitude and not pitch down. It's impossible. They just can't do that. Remember, pilots claiming to just follow an altitude is not proof for the claim that they are flying over a globe Earth, as they would have to do exactly the same thing if they were to fly over a flat Earth. And any corrections being made for altitude in reality is due to weather, their direction and the time of year, as they will be encountering weather systems and convection cells, things that will be constantly changing from place to place and season to season. So following an altitude is not a proof of a globe Earth. Where would you even get an altitude reading from on a globe Earth? Anyway, so the point here is that like a lot of pilots will say, well, I just follow an altitude and that brings me around the globe. No, that's not how it works. Excuse me. My throat is dry from talking. So that's not how it works. You can't follow an altitude but not pitch down. You're going to have to not be pitched up. You're going to have to be every second pitched down by 0.0025 degrees, right? That will accumulate as 9 degrees below your original horizontal after 1 hour. So 1 hour later, your airplane has to be pitched, right? The chord line and the nose of your airplane has to be pitched 9 degrees below your original horizontal. So there is only one horizontal. Horizontal is a constant. That means you have to be an hour later, once you've taken off, however you do that on a globe, I don't know. Once you've taken off and got up to cruising altitude, you're going to have to, right? You're going to have to be, after an hour, at least 9 degrees below if you're flying at 550 miles per hour. Yeah, at least 9 degrees, because you have all the takeoff issues on a globe and all that as well. That's it for the separate argument. But the point is that you can't avoid that, and that's only 1 hour. So there's no way that you can avoid going below 0 degrees horizontal. You can't do that. There's just no way to avoid that if you're claiming to follow an altitude around the globe or to fly around the globe Earth with a radius of 3959 miles at 550 miles an hour. There's no way to avoid it. And the point is, over a flat plane, you'd have to follow an altitude just the same, right? And okay, that altitude may change a bit here and there with weather and convection and stuff like that. You know, if you're flying over the United States and it's summertime, there's going to be more convection, so your altitude might raise a bit in the south and might lower a bit in the north. But if you want to hold the same altitude as, because I'm sure convection cells and all that do affect altitude for an airplane as it's flying, because the air pressure will change due to the convection. But if you want to follow a particular air pressure, but I mean, other than like weather and stuff like that, you're basically going to be trying to hold the same air pressure above the ground underneath. And anyway, on a globe, where would you even get an altitude reading from? You'd have to have you'd have to have air pressure in the first place. How do you have that on a globe? You don't. It's impossible. That's another physics impossibility. So, if we were to take a flight from London Heathrow to Los Angeles International (LAX), you would be flying at cruising altitude for close to 11 hours. I know this, I was on that flight myself several times. So if you flew this route over a globe Earth with an average radius of 3959 miles while travelling at an airspeed of 550 miles per hour, then you would have an accumulated pitch down below horizontal of -9 by 11, or -99 degrees from your starting horizontal. And do pilots do this? No, the end. So pilots don't, right? They don't fly at 550 miles per hour, right? Between London and LA, and and account for -99 degrees below horizontal pitch. They don't do that. I've been on that flight 4, maybe more times, and every time, right, the airplane has the nose and the chord lines pitched above horizontal, always. There's no -99 degree below horizontal pitch accounted for. That does not happen. They can't follow an altitude and fly as they do in reality. So they can't follow an altitude. Sorry, they can't follow an altitude and fly around the globe and fly as they do in reality. Either in reality they fly pitched up and they follow an altitude over a flat plane, or they pitch down constantly and follow an altitude around the globe. Right? It's either one or the other, and there's no evidence that they're pitching down because to follow an altitude around the globe, because they will be losing positive lift, which means they can't fly, and they're in a descent, right? So they don't do that. So I'm just going to show something here, right? Right. So 0.0025, right? So that is minus 0.0025% of a degree, right, below horizontal, that they would have to pitch down for or count for every second. So if I multiply that by 60, right, we get minus 0.15%. They'd have to be pitched down every minute. Multiply that then by another 60, right? That'll be 9 degrees, right? So for the flight from London to Los Angeles, you're talking a minus 99 degree below horizontal, below your starting horizontal. You'd have to pitch down 99 degrees below that, right, to follow an altitude around the globe Earth, or to fly around the surface of a globe between London and Los Angeles, right? But the longest flight in the world, I think, is 21 hours. I think that's what it is now. I think it's New York to Perth or London to Perth, one or the other. So if we, sorry, I'll put that there again. So if I go 9 multiplied by 21 equals 189, right? That's 189 degrees. You would, the pilots, 189 degrees, the pilots flying for those 20 hours would have to end up 189 degrees below their starting horizontal. The pitch angle would have to be 189 degrees below it. Do you think that's happening? I know it's not happening. Nobody is 189 degrees below the horizontal they started flying at. Not when airplanes have to fly with the chord line and the nose of the airline. Not when pilots have to fly airplanes with the chord line above horizontal, right, by several degrees to fly horizontally. So to go in a straight line, not a straight line, but horizontal line, not just straight, but horizontal. To fly horizontally, the pilots have to pitch up above zero. They have to. That's the only way they can do it. So how could they be ending up 21 hours later with a pitch angle that's 189 degrees below their initial horizontal? How do you violate horizontal? You can't. It's impossible. You can't go from one horizontal, then make up a different one a while later. That's not reality. That's not how reality works. There was one horizontal and it's always a constant. So none of this is happening. So I don't know what to say to anyone who still believes they live on a globe. There is no evidence that aircraft are flying around a spherical surface. So there was just zero. So take it or leave it. It's up to you.